the files. We'll go over that in class, but there's a, I don't know what the official rules are called, but the rules are actually in place for a good reason, because it might be the case, folks, that your face may appear on some video somewhere. I mean, if you're sort of face in front, it's not likely that will happen, but you know, if you get up or you're walking late or something, you might appear on an archived video for this class, and this just says, if you're uncomfortable doing that, then, I don't know, wear a mask or something, or sit in the back, or sit behind the camera or something. I mean, we're trying to make it so that, especially in a class like this, where I know some of you have full-time jobs, or maybe you're already teaching in schools or something like that, and you get off work and your car breaks down, or the traffic's too bad, or you just got something that, work takes you out of town, something of that nature. At least this way you have the chance of, heading onto the internet and watching me yammer around. Whoever is going to be recording this class, Nick, I know it's going to be you tonight, but student is going to have to be sort of like, because I do this a lot. Anyway, it'll be fun. Okay, let's officially start. My name's Gene Abrams. Feel free to address me any way you'd like, whatever you're most comfortable with, either Gene or Mr. Abrams or Dr. Abrams or Professor Abrams, or I don't really care. Whatever whatever sort of is most comfortable for you. There is a website that'll support this course. At that website, I'll try to sort of rig it that will link you directly to these video things, but there'll also be a direct access to the video stuff as well that I'll talk about on Wednesday. I'm officially in my office before class for essentially a half an hour, and then it takes me about 10 minutes to wander over here, so if you're in my office, we'll sort of break at 4:20 to walk to class. I'm also in Tuesdays and Thursday afternoons for a couple of sessions. I actually teach a class in between those two sessions. That's why there's a chunk in there. And every day by appointment, so if you need to see me, please feel free to stop by. Or probably the best thing to do is send me an email and try to make an appointment, and then I can guarantee that I'll be in my office at a set time. Also, for what it's worth, and this seemed to be popular 2 years ago when I taught a class in here, I'd go right from here to the bus stop, because there's a city bus that I take home, leaves at 6:05, so there's like 20 minutes or so in between. So if you want to sit with me at the bus stop or something, just grab me after class for 10 minutes right outside here. I'm more than happy to answer any questions you might have or point you in the right direction on a problem you might be working on. So please feel free to take advantage of that. This supplemental instruction sessions with Jen Holmes, I'll talk about those more, especially in the context of homework and exams, so let's hold off on that momentarily. The text is, let's see, is this one? Yeah. Text by Fraley. It's a classic by now, actually. I think the first edition was 30 years ago or something, and he has updated it appropriately. He includes some stuff about cryptography and various interesting questions about algebra that have come up over the recent years, some of which have been solved. We'll talk about some of those over the course of the semester. There, I know, is like a international version or something like that, or something you get out of London that's a little bit cheaper. Someone showed me that actually last year when I taught this course, and it seemed to be identical, but there's no guarantees if you try to buy something that's a little bit non-standard. Plan on 3 exams in here, and here's how they will work. There'll be 2 standard 75-minute exams, exams 1 and 2. I list the approximate dates that those will be on. Approximate means, barring a snowstorm or I have to cancel class one day or something like that, it should be on those dates. You'll know 2 weeks in advance when the exact date's happening. It's not any sort of mystery. So I can't say on day 1 exactly when they'll be, but I'll give you plenty of advance notice so that you can prepare for those. Exam 3 will be essentially just another 75-minute exam. It'll cover the last third of the course, but it will be given during the final exam period in here, which happens to be Wednesday, December 12th. It's also the case that during the final exam period, Wednesday, December 12th, if you so choose, you can also take a second 75-minute exam during that 2.5-hour period. That second exam will cover the material that was covered on exams 1 and 2 together. And the way it works is, in the end, each exam is worth 30%. But I've talked about 4 exams, so that doesn't make any sense. You have to count exam 3, the one that you take during the final exam period. And then of the remaining 3 exams, you count your best 2. So if you do really well in exams 1 and 2, there's really no reason for you to take this sort of optional final during the final exam period. You just walk in, take exam 3, and leave. But if you don't do so well in either exam 1 or exam 2, you have sort of a chance to make it up at the end. I'll talk about this more in a little bit. That's, the nature of this course is sometimes it takes a little while for the sort of general idea to sink in, and some students stub their toes on exam 1 and then just start, the light sort of goes on in week 6 or week 10 or something like that, and so this sort of gives you a chance to maybe make that up at the end. Okay. Yeah, and let's see, it says here, I'll explain this in more detail as the final exam date draws nearer. Don't miss an exam. I mean, in effect, if you miss an exam, folks, then you're obligated to take this final exam. That's how you make up. So I'll just count it as a 0, but you get to replace that 0 by whatever happens on this final. Okay. The most important thing that you can do in here to prepare for the exams is to do the homework in such a way that you really understand the material. So here's how homework and a few short quizzes are going to work in here. The way homework, or the rhythm of homework, will be this. I'll give you an assignment essentially every Monday. The assignment will include problems that I'll cover that Monday and probably the following Wednesday, so that week's worth. You should start on those right away. Admittedly, not all of them might be familiar because some of them cover. And then you, in effect, have a week to do the assignment. It'll be due the following Wednesday. Okay? So stuff that I assign today will be due a week from Wednesday. Yeah. So I've tried this 2 different ways, and this is the first semester I'm going to try a little hybrid. So up until a couple years ago, it was always do the homework by yourself, in the sense that I want you to actually write up your own homework assignment, turn it in. I always encourage you to work with other people, and I'm still going to encourage you to do that, and I'll talk more about those details in a minute. But if you'd like to work together in a group of either a group of 2 or a group of 3, and you'd like to, as a group, submit one assignment from your group in such a way that, when I grade it, everybody in your group will receive that same homework score, that's now going to be fine. And you can sort of mix and match groups. You just make sure that at the top of the paper you'd write down, this assignment is from this person and this person and this person, maximum of 3. So if you feel like you're better off understanding material by working together in a group, more power to you. That's good. If you feel like you're better off working alone, good for you too. So, if you know some friends in here, or probably most appropriately, if you go to some of these supplemental instruction sessions and you wind up working with someone in there, you might say, hey, let's do this assignment together. And if it's a mutually agreeable situation, then great, and if not, not to worry about it. If you decide to work together for one assignment and you turn that one in and you decide that just didn't work out very well, then fine. The next time you can just turn them in yourself. So there's no, you can sort of mix and match as you see fit over the course of the semester, whatever you'd like to do. The homework will be graded on a 10-point scale. That means that you're going to turn in a certain body of work, and there won't necessarily be 10 problems, but I will grade it out of 10 points, 10 being the maximum. When you do the homework, I'm going to pass around some information about what I expect to see when you turn in a homework assignment. What I'm looking for is complete answers. I'm looking for a strong indication that you really understood what the issue or the essence of the question was, what the tool or technique to get to the solution is, that you've written it up clearly, not clearly in the sense that, well, the instructor will understand what I'm talking about, so I'll just sort of scribble something down and let him figure it out. Clear in the sense that your homework solution should be written in such a way that if your solution was to be included in a student solution manual down the road, that it would fit that bill well. That some other student who presumably doesn't know what's going on would be able to read through your solution to a given problem and say, oh, now I understand what's going on. Okay? So I write up and give you lots of detail about, how to turn it in, what it should look like, what sorts of things you should be wary of or sort of be on guard for. My philosophy on the homework is anything goes. I mean, almost literally anything goes. If you want to work together, that's great. You want to come and ask me questions about the homework before it's due, that's great. You got somebody that you know that took the class before, that's great. You got a solutions manual or something like that, that's great. I mean, whatever it is, it's just, you're going to have to pay the piper once the exams come around. So if you've just sort of done the homework in sort of a slapdash way and just thrown it together, all right, maybe you'll get pretty good homework scores, but then you'll fall flat on your face. So, you're all adults in here. You know how you best learn, and if you best learn working with someone, great. If you best learn locking yourself in a closet and just banging your head against the wall, then some of us do. Sorry. Okay. Anyway, whatever it takes for you to get it done, get it done. What I've included is a little paragraph about who you should be writing your homework solutions for. I guess that would also include your exam solutions, but more importantly your homework solutions. And then I've also included some stuff on the back here that indicates some errors that I typically wind up seeing when students submit homework for this course. Typically the errors look like you start with what you want to prove, or you wind up proving that 1 equals 1 and somehow using that to conclude that what you tried to claim is true, or you wind up getting through a proof and you in the end have somehow left out one of the hypotheses of the proof. That typically means warning light should be going off, that you've missed something or you've made an inappropriate step or whatever it is. So I've listed some things there that you might want to read through before you start turning in homework assignments. Okay, let's see. What I want to do is get some sort of idea of what your collective backgrounds are. So I'm going to send around a sheet where I'm asking for your name, your email address, your major, whether or not you've taken the number theory course, the Math 311 course, and just, I know that a lot of you took the number theory course from me last spring, but either put no or put when you took it. And then I list other algebra. I guess that could include Math 313, although I'm going to assume that all of you have taken the linear algebra course. But for example, if you've taken the Math 413 course, the more advanced linear algebra course, or if you've taken maybe a combinatorics course at another university, something like that, just list that out in this last column here. What I'll be doing for what it's worth is I'll make an email list. I know that a lot of you don't either use or check your official UCCS email. That's why I'm asking for this thing. And then, if there's a snow day or if I have to change something or something like that, then I can send out a blanket email in addition to putting information on the website. Okay. Let's see, quick quizzes. There'll be about a half dozen quick quizzes over the course of the semester. For instance, if there's a particularly important idea or theorem or definition that I want to make sure you have immediately here. What I will tell you the class session before is there will be a quiz. The next class session, it'll take the first 3 minutes of next class session. I will tell you exactly what's on it. It'll be give the definition of a group, or give 3 equivalent conditions to a subgroup being a normal subgroup, or just something like that. There's no mystery here. It's just do this. You have to do it because you need to have this stuff, in solid. And so those will count like homework assignments. And again, there will be no mysteries there. Just you'll need to know this stuff, so I'll just ask you to come in and have it memorized. Grading system. When it's all said and done, when you count the exams at 30% each, modulo that deal about allowing you to drop either exam 1 or exam 2 in place of this quote-unquote final exam, and you count the homework at 10%. If you're up over 90% of the points, then you get an A. Maybe it's an A minus if you're at 90.1% or something like that. But you're guaranteed to some sort of A. If you're up over 80%, you're guaranteed to some sort of B, etc. That's an if-then statement, but the converse is not necessarily true. It might be the case at the end of the semester when I sort of see how you did as a class that, there's a bunch of you clustered at 90.1 and one of you at 89.9 or something like that. Well, the 89.9 would be an A minus too, or maybe an 88.7 would be an A minus. So I could drop it, but I can't raise it. That's, it means that everybody could be rewarded in here. If you all do well and you understand the material, there's no reason for me not to give lots of A's, and I would be very glad to do that. I mean, I'd be very glad to do that. So, if nothing else, that it's sort of consistent with my homework philosophy too. You're working together on the homework. You're working together to understand the ideas in here. You're not trying to be in competition with each other. I mean, I don't know, you make a small side bet or something like that before an exam with your buddy. But modulo that, there's no quota of grades or anything like that. So, okay, and then a quick remark about administrative dates. If you decide after the first 2 weeks or so that this isn't the place for you to be, then you have to get out by September 6th to get all your money back and all that good stuff. And then if by about mid-semester, when is that, about week 9 or week 10 or something like that, you decide it's really just not working out, then you can still withdraw, but I need to sign. And there's no class 2 weeks from today, or the Wednesday before Thanksgiving. All right. Questions? Comments? All right. Well, hopefully, typically in the senior level classes where I'm grading the homework, I grade the homework in here for what it's worth. By passing the homework back, I typically can learn your names by the end of September or so, and I've got a relatively good head start in here. Okay, so I've got about 10 already. That's good. Okay, so if you come in my office or you come up after class, do me a favor, just introduce yourself. Hi, I'm whoever you are, and just say hi. And once I've associated a name with a face, it's typically not too hard for me to keep it in there for the rest of the semester. Okay. Books. Books are available? Not available? Okay, we're all right on books. I don't need to call the bookstore and tell them to order more. If that happens that they run out, let me know and I'll try to make sure that they get more in soon. Okay, so twice in the past, twice in the last 5 times that I've taught this course, the students have voted to do a note-taking co-op where one person per day is designated as the official note-taker. That person then brings their notes to me the next day, let's say, after they've polished them up a little bit. I look through them to make sure they're mathematically sound, and then we post them in the library on reserve so that if somebody's missed the class, they at least know what's going on. And we've got 20-something-ish students in here, so if there is a note-taking co-op, essentially you'd have to volunteer just to do once per semester. But we have this video archiving now, so it's not clear whether that maybe minimizes the need for a note-taking co-op. But I'll say this. If you'd like to have a note-taking co-op, we'll take a vote on Wednesday. And if at least half of you, that means at least 14 of you, vote to do a note-taking co-op, then I'll ask the entire class to do the note-taking co-op, and we will then assign you a date. We'll just pass a sheet around or something like that. But hey, if you vote not to, that's fine too. Just think about it for a couple days, and we'll do that at the beginning of Wednesday just to see if there is interest in that. There's plus and minus. You only have to put in 1 day's worth of. It's not really much work if you're going to take notes anyway. You just have to polish them up after class and get them to me. That way, at least there's a written version of what goes on. One slight disadvantage with this videotaping is, you see what I'm going to write here, but you don't really have any access to a place on the net where you can just print off 3 or 4 pages of notes or anything like that. Is that right, Nick? Yeah. So, oh well. Okay, so what the heck is this course? Algebra. So you've been in an algebra course since, since 6th grade. You probably saw your first algebra course. I'm guessing that most of you, well, not most of you, I'm guessing that a significant percentage of you have actually taught algebra in the high school, so you're thinking, well, I don't know what algebra is. Yeah, you do. You've at least seen some pieces of what we're going to do in here this semester. Probably the best way to intuitively think about what modern algebra is, or some people call this abstract algebra, but after a while it becomes very concrete, so I don't really like the title of this text. We'll call it modern algebra. The real idea is to look at certain systems where it makes sense to somehow combine things in the system and produce another thing in the system. You know a lot of those systems. You take 2 real numbers, you add them together, you get another real number, subject to certain conditions. You take 2 whole numbers, integers, you add them together, you get another whole number. So there's one. You take 2 sets, and you form their union. You get another set. That's pretty good. So, we've seen in your life lots of different systems where you can talk about adding things or combining things to get another thing in the system. Hey, there's nothing special about adding. How about multiplying? You take two whole numbers, you multiply them together, you get a whole number. Take two real numbers, you multiply them together, you get a... You take two 4x4 matrices and you multiply them together, you get another 4x4 matrix. You take two vectors in a vector space and you add them together, you get another vector in the vector space. So there's lots of systems out there that at their heart really are just systems where you've got things. I don't know what the things are. They might be functions or real numbers or complex numbers or matrices or vectors or da-da-da-da-da-da. But in all of those systems, you talk about combining two things in the system to get another thing in the system. And that's really what algebra is about. Now, I mean, the types of systems that I just described seem pretty general. Yeah, there's lots of systems out there where you can talk about taking two things in the system and combining them to get another thing in the system. Not all of those will be captured by what we're going to study this semester. We're going to study systems that, well, in which you can combine things, but that have certain additional properties. Let me intuitively give you one. If I talk about, let's just do, if I talk about the positive whole numbers, the positive integers, 1, 2, 3, blah, 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 blah. Okay, so there's the system. 1, 2, 3, blah, 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 blah. Let me give you an operation, a way to combine two positive whole numbers together, a positive whole number, multiply them. Take any two positive whole numbers and multiply them together, you get another positive whole number. So there's a system of the flavor we're interested in. It's also the case that there's a special positive whole number called this, with the property that if you take this and you multiply it by anything in the system, it doesn't change the other thing. We'll call that an identity element for the system. Okay, under multiplication. All right. Well, let's talk about another system. How about the positive real numbers? So the real numbers that are bigger than 0. And the operation there is multiplication. That's another system. You multiply any two positive real numbers, and you get another positive real number. No big deal. And that system has a special element. It's also called this. Of course, you can call it 1.0 depending on what the form of the things in the system is that you're asking me to look at. So anything that looks like a positive real number, you multiply by this thing, you get this thing back. All right. So the two systems, at least at the level that we've looked, share similar properties. The positive whole numbers, it's a closed system under multiplication and has a special element in it that acts as an identity. And the positive real numbers has the property that's closed under multiplication, has a special thing in it that acts as a multiplicative identity. But here's where the two systems differ. If you hand me something in the first system, like the number 3, is there something else in the system that you can combine with 3 to get the multiplicative identity? Can you find a positive whole number so that when you multiply it by 3, you get 1? Well, of course not. If you try to take a whole number, you multiply it by 3, you're certainly never going to get 1. You might say, well, how about 1/3? Good choice, but 1/3 is not a whole number. It's not in the system. On the other hand, if I'm looking at the positive real numbers, if I hand you any positive real number, I can always find another positive real number so that when I multiply the two things together, I get the multiplicative identity of the system. So there is a property or a piece that is true in the second system that isn't true in the first system. And if you want, what you've just seen is a glimpse of the type of analysis that we're going to do on systems. Here's a system. Yeah, it's a system. Here's an operation. You combine two things in a system to get something back in the system. But certain systems differ from other systems. Some systems have multiplicative identities. Some systems don't. Some systems have the property that if you look at something in the system, you can always find something else so that when you combine it, you get the multiplicative identity. Some systems don't. And what we're eventually going to do over the course of this semester is the following. There are two very important types of systems that we will study. One is called a group. That's the first type of system. And the other is called a ring. The notion of a group we'll look at for 8 or 9 weeks or so. The notion of a ring we'll look at for the remaining 6 or 7 weeks of the semester. In effect, these two things are simply nice systems that have the property that they look relatively general. So when we write down the underlying characteristics that describe what a group is, not every algebraic structure is a group, but certain things are. Enough things are groups that merit us discussing or somehow studying those in their own right. We'll look what sort of properties they have. We'll look at a lot of examples, and we'll see what sort of structure we might be able to conclude from that. We'll then look at the notion of a ring. A ring, in effect, folks, is an algebraic system that has two types of operations defined on it. Like if I hand you the collection of all integers, it makes sense to add them. It also makes sense to multiply. Similarly with real numbers, similarly with square matrices, similarly with functions. So there's lots of systems that have more than one operation. Systems with two operations that behave nicely, those systems will be called rings, and then we'll analyze those systems. So that's the general overview of what we'll be doing in here. What I'll try to do is at least point you in the right direction if you're interested in how these particular structures might, I don't know, be applicable in the real world. That's a totally great question, and I'll at least try to, point to places on the internet or places in the text where they talk about that. But what I'm more interested in doing, because I know that there's a lot of you in here that are potential teachers or are already teaching in the high school or the junior college level maybe, is I want to make sure that you take a lot of the ideas that you've seen, that you're familiar with, certain properties of algebra, typically algebra of the real numbers, and show you what's really driving those behind the scenes. What is it about the real numbers that makes it so interesting? Or not interesting? What is it about the whole numbers, the integers, that somehow both makes it interesting but makes it different from the real numbers? What is it about the complex numbers? What is it about the et cetera, et cetera, et cetera? So there's lots of algebraic systems out there that you're already familiar with, that you're probably talking to or teaching to about in your classrooms. And what I'm hoping to do is just make sure that some of those ideas become a little bit more solidified in your mind as to where they come up and why they're useful, etc. So that will be a main goal of this semester, is to try to give you some tips or some good overviews for those of you that are going to be teachers. Okay. All right. So let's start. Before we get to the first main idea, which is this, we'll probably get to it on Wednesday. What I want to do is review some ideas that you have seen before, either in the discrete math course or in the number theory course or in the linear algebra course. If these are new to you, I'll give you enough of the detail that you can pick it up here for the first time, and we'll be doing some problems for homework on those. But for most of you, I think this is going to be a review. So, review of some important concepts. The first is what are typically called equivalence relations on sets. Equivalence relations. When I teach the discrete math course, I like to present these as what I'll call generalized equality. The idea is this: you have a set, and I don't care what the set is. It might consist of numbers, but it might consist of functions or matrices or people or license plates or whatever it is. It doesn't matter what the underlying set is. The idea is, let S be a set. Then we define a relation on S is simply a way of connecting elements in the set. Elements of the set. I'm purposely being nebulous here. If the set is license plates, then the difference of the two numbers is even. If the distance between them is some even number, that's a way to connect them. All right. Typically, the symbol that's used for one thing in the set is related to another thing in the set is either this tilde symbol or sometimes the letter R. And here then is what we mean when we talk about an equivalence relation. An equivalence relation on a set. Relation on a set S is a relation, I don't know what you want to call it. How about let's call it R for relation, that has the following properties, where the following three things are true. First of all, for every element in the set, let's call it little a and capital S, every element is related to itself. So whatever the determination of how it's supposed to be decided whether or not one thing is related to another, in order for the relation to be an equivalence relation, it has to be the case that every element is deemed to be related to itself. So for example, if the relation on the collection of license plates is deem one license plate to be related to another if the first symbol of this one is the same as the first symbol of this one, folks, if you hand me the same license plate twice, then obviously the first symbol of this one is the same as the first symbol of this one. There's nothing. Or if the relation is on the collection of people and we deem two people to be related if they have the same eye color, well, if you look at the same person twice, does that person have the same eye color as that person? Well, of course, it's the same person. So that's the idea behind this particular stipulation in an equivalence relation. Secondly, for every pair in the set, we'll call them A and B in the set capital S, if it happens to be the case that A is related to B, so if one thing is related to the other, then necessarily B is also related to A. So for example, on the set of real numbers, if you deem one thing to be related to another in case the first one is less than the second, if the first one is less than the second, then you don't have the second related to the first, because we're talking about one thing being related to another if this one's less than that one. And if you've told me A is less than B, then it's certainly not the case that B is less than A. So this is something that might be true for some, might not be true for others. Let's go back to the license plate example. If you deem two license plates to be related in case the first letter of the first one is the same as the first letter of the second one, well folks, if the first letter of the first plate and the first letter of the second plate are the same, then the first letter of the second plate is the same as the first letter. In other words, there, it doesn't matter which order you hand me them in. And the third stipulation, if we're going to call a relation equivalence relation, is the following. If it's the case for every three elements in the underlying set, if A is related to B and B is related to C, then A is related to C. And these three conditions are typically given the three names. This is called the reflexive condition. This is called the symmetric condition on a relation, and this is called the transitive condition on a relation. So the punchline is this: if we have a relation on a set which is reflexive, symmetric, and transitive, then we call the relation an equivalence relation. There are numerous examples of equivalence relations. Example, let's just give an easy one maybe. The set is the collection of cities in the United States, in the U.S., and maybe the relation is deem one city to be related to another city in case the two cities A and B are in the same state. Okay, so Colorado Springs is related to Denver. Colorado Springs is not related to Chicago. Because the definition of what it means to say that one city is related to another is you simply ask whether or not two cities. All right, now we can just quickly click through this. Let's see. If I hand you the same city twice, is a city related to itself? Of course it is. It's in the same state as itself. If a city is related to another city, is that second city related to the first one? Yeah, because if you tell me that one city is related to another, you've told me that the two are in the same state. So does that mean the second one is related to the first? Yeah, because they're in the same state. And finally, this transitive condition is easy as well. If city A is in the same state as city B, and city B is in the same state as city C, is city A in the same state? Sure. So this is an equivalence relation. Then R is, and I'm going to start abbreviating this by ER, equivalence relation, on the set capital S. Example, the set S is the collection of, let's do the example now, is the collection of, let me give you this notation now. capital Z with an extra line. Capital Z for the remainder of the semester will denote the set of whole numbers, which I'm going to call integers. That's the formal word. Positive, negative, and 0. Positive, negative, and 0. Okay, so this is negative 10, negative 9, etc. All of the whole numbers. I'll do a little history in here too. The YZ, what the heck is that? It turns out, historically, the study of what we now call modern algebra, but I'm just going to call algebra for the remainder of the semester. I'm never going to call it abstract algebra. As a discipline, started in earnest in the German school in Göttingen in the mid to late 1800s. And it turns out the German word for number is Zahl, Z-A-H-L, so that's a number, and plural is Zahlen. And so the German school started using this as a very natural symbol for the collection of numbers. And it turns out that that school's influence has been powerful enough that this notation is totally standard throughout most of mathematics today. If you look at the set capital Z, or sort of boldface capital Z, that typically is understood to always be the set of whole numbers. Here's a relation, deem the relation A is related to B in case if you square the first one, you get the same as the square of the second one. So that's the definition of a relation. I've just sort of cooked this up. I won't say out of thin air. I mean, I've had this in mind because it's got certain properties to it. So, for example, 1 is related to 1, for instance, because 1 squared equals 1. 1 is also related to minus 1, because 1 squared equals minus 1 squared. So there's 0 is related to, what's related to 0, but it's not related to anything else. There's no other integer that has square 0. Okay? Then it turns out script R is an equivalence relation. I already broke a promise. I was going to abbreviate that by ER. I just wrote it out. Why? Well, I won't run through all the details, but it's pretty easy to see. First, is it the case that every integer is related to itself? In other words, is it the case that A is related to A? Well, in order to test whether or not A is related to A, you have to decide whether or not A squared equals A squared. Check. It sure does. Question, if A is related to B, in other words, if A squared equals B squared, is it the case that B is related to A? In other words, if A squared equals B squared, does B squared equals A squared? Well, yeah. And finally, if A squared equals B squared and B squared equals C squared, does A squared equal C squared? Yeah. So that's pretty easy to check off there. Let's give a non-example. Non-example. Let's let the underlying set again be the integers, although it doesn't really matter. I could let this be one of any number of sets. Define the relation R by A is related to B in case A is less than or equal to B. So here's what it means for the integer A to be related to the integer B. You deem them to be related in case this one's less than or equal to that one. So 3 is less than or equal, so 3 is related to 7, for example. Okay, that's good. So let's see, is this an equivalence relation? Well, is it the case that every integer is related to itself? In other words, is it the case that A is less than or equal to A? Yeah, that's good. How about the second one? Is it the case that if you hand me A related to B, is it necessarily the case that B is related to A? The answer is no. If you tell me A is related to B, then what you've told me is A is less than or equal to B. Does that imply or necessarily yield B related to A? Well, no. If A is less than or equal to B, it's certainly not necessarily the case that B is less than or equal to A. It might be if you've handed me A equals B. But for instance, 1 is related to 2, but 2 isn't related to 1. So this is not symmetric. And now, here's a habit that I want you to get into. If it's the case, folks, that you've got some system or some list of requirements for something to be a, well, here, something to be an equivalence relation. Later on, we'll have a list of requirements for something to be a group, for something to be a ring, for something to be a subgroup, for something to be a normal subgroup. We'll have a list of requirements. Here's what it means for this to happen. If the requirement includes some sort of stipulation that for every blah, 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 in order to convince me that the proposed system isn't one of the flavors that you're looking at, all you need to do is come up with one specific counterexample. Just one, and then you're done. So I can convince you that this relation is not symmetric by simply coming up with just one situation where this isn't true. Why? 1 is related to 2, but 2 is not related to 1. Done. Okay? So this is not an equivalence relation. So R is not an equivalence relation. All right. All right. Let's look at a few more that are. Questions? Sorry? Question?
Is there ever a situation where you want us to continue to disprove once you find one small just
I understand the question. Yeah. So if the condition that you're trying to decide whether or not it's true or not consists of more than one property, as soon as you find one where it's done, then you're done. Don't worry about trying to show that other things are true or not. So, in fact, that'll come up in the definition of both group and ring and subgroup, and there'll be more than one condition that a thing needs to satisfy in order to call it a whatever we're calling it. As soon as you found something that doesn't hold, just walk away. Say it's not this, therefore it's not a group, or it's not a ring, or it's not. All right, example. This is an important example that we'll see later. Example, the set is, again, the set of integers. And here's how we're going to deem the relationship. Define a relation R by setting A related to B in case when you look at the difference B minus A that you get a multiple of 4. This one's a little bit more interesting. Now I have to define what it means by a multiple. When we're talking about whole numbers, the understanding is to say that something's a multiple of another whole number means that you have to be able to take the original number that you're handed and multiply the number 4 by another integer. So for instance, I don't want 7 to be a multiple of 4. You might say, well, it is. You take 4 and you multiply it by 7/4, you get 7. Not allowed. When we talk about integer multiples, we mean that the thing that you multiply has to be another integer. So I'll put in here for now an integer multiple. But that's going to be understood from now on when we're talking about the underlying system being the system of whole numbers. So this is sort of interesting. Two things are deemed to be related in case when you take the second one, you subtract the first one, that the number that you get is a multiple of 4. And it turns out this is an equivalence relation. Sort of interesting. Let me briefly go through how you might prove this. Proof. Let's see, we have to show first that this relation is reflexive. We have to show that A is related to A. I'll use this symbol, you'll get used to it, for all integers in Z. So the upside down capital A is a shorthand that represents the phrase for all, or for every, or for each. This is the for all quantifier. We have to prove that. That's one of the requirements of being an equivalence relation. All right, well, let's see. So, A related to A, question mark. So, what do we need to determine in order to decide whether or not A is related to A? We need to decide that if we take the second thing, there it is, it happens to be called A in this case, and we subtract the first thing, this just happens to be A also, is 0. So that's what we get when we do the second minus the first. The question is that an integer multiple of 4? In other words, can I take 4 and multiply it by some integer and get 0? Well, sure, because it's 0 times 4. So check. A is related to A. I've shown that if you take whatever the appropriate prescription is, here it's you take the second number, you subtract the first, that what came out is a multiple of 4. Happens to be 0 times 4. That's fine. Therefore, the appropriate condition is satisfied, and therefore the particular relation is indeed reflexive. How about the next one? Secondly, if A is related to B, do we get, or can we conclude B is related to A? In other words, is it a symmetric relationship? So what you get to do here is assume A is related to B. So we get to assume what? A is related to B means that B minus A is, and let's write it out formally, is a multiple of 4. Let's call it 4 times n for some integer n. That's just the definition of what it means to be a multiple of 4. That you can write this number as 4 times some whole number. And what do we need to do? We need to show, this is what we're trying to conclude, that B, pardon me, we're trying to show that when you take the thing on the right, which here happens to be A, and you subtract the thing on the left, which happens to be B, is 4 times some other integer for some integer t. This is what we're given, and this is what we have to show. Well, how do you get from here to here? Sometimes it's not so easy to see. Here it is pretty easy to see. Take what you know. We start with this. That's what you get to assume. Well, because it's a given equation, you can manipulate both sides of it and get to here. But if we start with b minus a equal to 4n, multiply both sides by minus 1, folks, that's legit to do because this equation is assumed to be true. That's given information. Well, if I multiply the left side by minus 1, I get a minus b. If I multiply the right side by minus 1, I get minus 4n. Which doesn't tell me what I need to know yet. What I'm trying to do is convince myself that a minus b can be written as 4 times some integer. So now rewrite, just use some arithmetic. A minus b is 4 times minus n. I've written minus 4 times n as 4 times minus n. That's just arithmetic. But then this is okay. Equals 4 times t, where t is minus n. And so, check. So I've concluded the appropriate equation is true. I've shown that a minus b is 4 times some integer because if n is an integer, then necessarily the negative of an integer is an integer. I guess I officially haven't written out everything. I'd probably like to see a statement like that in your homework. Why is it the case that I've written a minus b as 4 times t, where t is an integer? Because I've written it as 4 times minus n, where n is an integer, and if n is an integer, then the negative of n is also an integer. All right, that was easy. Step 3, we'll do it a little bit more quickly. You get to assume what? A related to b and b related to c. What you need to do is show that a is related to c. Presumably what we need to show in order to show this thing is an equivalence relation. Can we do it? Yeah, what are we assuming? We're assuming that, oh, b minus a is some multiple of 4. Let's call it 4 times n1. And we're assuming that c minus b is some multiple of 4. Let's call it 4 times n2, where n1 and n2 are integers. That's what it means to say that a is related to b and b is related to c. That's just the definition of this relation. And what do we have to do? We have to show that c minus a is 4 times some integer. Let's call it t for some integer t. That's the goal. So this is where we want to land. Quick remark, maybe because it's been a long summer and you haven't done any mathematics for 3 or 4 months or something. Folks, you can't start here. If on your homework you say, well, here's what I want to show, therefore it's true, and I'm going to start manipulating both sides of this equation, you will see a large red X, and you'll just get it kicked back at you because you've somehow violated this unfortunately common error that students seem to think constitutes a valid proof. If you're trying to conclude something, you can't start with it. You might say, well, if I start with it and I get to something like 1 equals 1, does not constitute a valid proof? The answer is no. You can't prove something is true by simply somehow showing that it implies something true. And some of you have heard the story before, because if you allowed that as a proof technique, then I'll be able to prove for you that 2 equals negative 2. Here's my proof. Proof that 2 equals negative 2. Proof 2 equals negative 2. That's what I want to show. Square both sides. 4 equals 4, which is clearly true, and therefore 2 equals negative 2. So this is where you have to land, folks. I mentioned this in the homework sheet as well. If somehow your conclusion is therefore 1 equals 1, that is not good. Because I'm not impressed by the statement 1 equals 1. I'm just not. I know it's true. You know it's true too, but so what? So what? I am impressed by your being able to convince me that c minus a is 4 times an integer. Let's see if we can do that. Well, I mean, I can show you the cute little trick here. That's true and that's true. These are assumed to be true, so I can manipulate with these because those are allowed in the system as true statements to begin with. So that means I can add both sides of these together, which would magically say that's cheating. Well, then the b's cancel and you get c minus a is, okay, I'll do that. Maybe another way would be, look, let's solve. What's c? c is 4n2 plus b. That's from the given equation 2. Arithmetic on a given equation. So let's see. And a is, if I solve for a, I get what? b minus 4 times n1. That's also arithmetic. I don't have to do it this way. Again, I'm doing it the long way, but I'm doing it in a way that maybe most of you would approach it. These are legit to write down. I can manipulate both sides of these because these are assumed to be true. All right, now let's compute C minus A. That's what I'm trying to say something intelligent about. Is what? Is 4n2 plus b minus A. Oh, A is b minus 4n1. Just substitute. I'll put that here if you want. Substitute. Which is by arithmetic. And I'm looking for each line to be at least denoted enough so that I know what you're doing, how you're getting from one line to the next. So this is 4 times, n2 plus n1. I believe you can do the arithmetic at this stage, folks. I don't need you to show me the minus of the minus. That's fine. Plus, let's see. Oh, b minus b, that's 0. That's nice. The b's cancel. So this is 4 times n2 plus n1, but this is an integer since it's the sum of two integers, and n2 individually are integers. I have to assume that here. So we boil it down to, you get 4 times the sum of two integers, so this is 4 times t, where t is an integer. It happens to be n1 plus n2. Check. That's what we were asked to show. We have shown that c. And I say, well, how did you do that? Well, look. Technically, there should be a follow-up statement, although we're mathematically mature enough that we don't have to put this level of detail in. I've then shown that C minus A equals this and justified Y, which in turn equals this and I've justified Y, and in turn equals this and I've justified Y, and in turn equals this and I've justified Y. So that, in effect, we've now shown that this equals this. So if you want to put one last line, is therefore C minus A is 4 times T as required, and we're done. All right. Now, anytime you have an equivalence relation, on any set, we've just seen one, this will be an important one, relations give rise to what are called equivalence classes. And here's how you get them. Once you've determined that you've got an equivalence relation defined on whatever set it is, and I don't care what the set is, I'm going to try to keep you away from thinking all the sets have to be numbers, but that was an important example here. What you then do is you look around in the underlying set and you ask what things are related to each other, and you lump all the related things together in a subset. So for example, we can ask this question: if I look at this relation that we just described, so on Z, A related to B if B minus A is a multiple of 4, is multiple of 4. So the relation, the equivalence relation we just looked at, we can talk about the equivalence classes. For example, if I hand you something in the underlying set, I'll just randomly pick 0 here. If I put then square brackets around an element, what I'm asking you to do is write down all the things in the set that are related to 0. Well, 0 is related to 0 because this is an equivalence relation, and anything is necessarily related to itself. What else is related to 0? In other words, what other things can I write down so that when I do it minus 0, that I get a multiple of 4? Well, 4 works because 4 minus 0 is certainly a multiple of 4, and 8 works because 8 minus 0 is certainly a multiple of 4, and 12 works, and negative 4 works because negative 4 minus 0 is negative 4, which is an integer multiple of 4. It's 4 times minus 1. Negative integers are perfectly legit here, etc. So what we call the equivalence class of 0 happens to be all the multiples of 4. We can talk about the equivalence class of 1. It's those integers that are related to 1, where this is the definition of the relation. Well, you can always start by writing down the element that you... what other things are related to 1? Those things, so that when you subtract 1, give a multiple of 4. 13, minus 3, etc. For instance, the equivalence class of 2, I'll let you write it out. 2, 6, blah, 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 blah. There's lots of things in there. Equivalence class of 3. 3, of course, is in there. 7's in there. And 11's in there. Minus 1 is in there, etc., etc., etc. And it turns out this is all of them. It turns out that every possible integer is included in exactly one of these equivalence classes. Every integer is related to exactly one of these 4 things. That's where the number 4 comes in. And for those of you that have seen the notation, what we've done is we've written down, in effect, mod 4 arithmetic, or we've sliced and diced the collection of whole numbers via their mod 4 remainders. And for those of you that saw the number theory course, what we've done is we've collected up all those integers according to what their remainder is in the division algorithm. So if you have remainder 0, you're in the first set. If you have remainder 1 on division by 4, you're in the second set, etc. Okay. Let's see. Let's get now to a set and an equivalence relation on that set, which is significantly more familiar to you. So here's a set. So a new set. I'm going to call the set S. It's the set of symbols that look like, let me call them C comma D. So the symbols in this set are inherently pairs, where C is any integer you want, but D is an integer bigger than or equal to 0. And I'm going to, for this class, use the notation capital N. This will be the set of natural numbers. And for me, this will include only the numbers 1, 2, 3, etc., etc., etc. It turns out that the discrete math book that's used at this university is actually a really good one, but they use a slightly different notation. For their natural numbers, they include 0. For me, the set of natural numbers will just be 1, 2, 3, etc. It turns out this is a more standard notation than the one that's used in the discrete math book, but neither here nor there. So there is the set. So I want you to look at all the things that look like ordered pairs, where the first thing is any integer you want, and the second thing is some positive integer. Like, minus 2 comma 7 is in this set, and the pair 17 comma 1 is in this set. The pair 16 comma negative 1 is not in this set because I'm requiring the second thing to be positive. So I'm going to define a relation on this set. Define on this set. And notice what the things in the set look like. They look like pairs. And here's the relation. If I hand you a pair, let's call it C1, D1, I want to deem that to be related to the pair C2, D2 in case when you multiply the outer two ones, when you multiply that times that, you get the same thing as if you would have multiplied the inner two ones, D1 times C2. So we're going to deem two pairs to be related in case that product, call it the outside product, is the same as the inside product. So for example, this pair 1 comma 2 is related to the pair 3 comma 6. Why? Because when you multiply the two outside numbers, you get the same as if you multiply the two inside numbers. All right, now, turns out, in the interest of time I won't prove this for you, it turns out it's not too bad to do. You'll do something slightly related to it when you do one of the homework problems. That script R is an equivalence relation. Relation on the set of pairs consisting of an integer in the first slot and a positive integer in the second slot. So let's look at some equivalence classes. So proof omitted. But what I want to do is look at some specific examples. I'm just going to pull these out randomly and look at various things that are in the same equivalence class of the particular pair that I happen to pull out. Let's, for example, find some things in the equivalence class of the pair 3 comma 2. So what does this mean? It means what I want you to do is write down some things that are related to this particular thing via this relation. So I need to somehow write down other things with the property that when you multiply the outside ones, that you get the same thing as if you multiply the inside ones. Well, look, this is an equivalence relation. So if I hand you something that's in the equivalence class, necessarily the thing itself is in there. Let's check that it is. This will be stupid, but it will be. Is 3 times 2 equal to 2 times 3? Yeah, it is. Okay. So it's no big deal. Let's see, what else? I need to rig something. Let me show you one that's in there. So that, is it the case that this is related to this? If I multiply the two outer things, 3 times 4, do I get the same as multiplying the two inner things? Yeah, 2 times 6. How about, somebody want to give another suggestion? How about 12, 8? Is that in there? Multiply the two outer things to get 24, the two inner things to get 24, so that's in there. How about, no, let's not do that one. Anybody see a pattern? And what would the pattern be? What does it mean to be related to the pair 3, 2? Yeah, it means if you take the first one, you divide by the second one, you get 3 halves. If I take 6 divided by 4, I get 3 halves. If I take 12 divided by 8, I get 3 halves. So it turns out, and hey, this follows directly from the definition there that C1, D1 is related to C2, D2 precisely when the fraction, I'll say as fractions, this symbol C1 over D1 is the same as the symbol C2 over D2. Now, why is that? Well, look, you just divide through. If these are equal, then. And, quick remark, it makes sense to divide by D1 and D2 because we've assumed that the things that sit in the second coordinate are natural numbers. In other words, they're bigger than 0. So these make sense. All right. So here's the point, folks. If I hand you this fraction, the point to be made is that fraction could be represented in other forms that don't just look like 3/2. It could be represented in the form 6/4 or 12/8. Or so the point is this: the collection of fractions that you're very used to dealing with really is a collection of pairs that come equipped with an equivalence relation on it. As a symbol, 3 horizontal line 2 is not the same as the symbol 6 horizontal line 4. This has got 3's and 2's in it. This has got 6's and 4's in it. So as symbols, they're not equal. But somehow you're asked to interpret those as representing the same thing in the system. Technically, what you've done is you've taken the collection of pairs where the denominator is not 0, and you've defined two things to be related in case this quantity is satisfied. So the punchline is a set that you have great familiarity with happens to be a collection of pairs on which an equivalence relation has been defined and in which you're simply comfortable with viewing things in the same equivalence class as somehow behaving the same way, as being equal. Now, that's all well and good, and you think, well, so what? You know, I know what the rational numbers are. Why is that an issue? This could be an issue, and in fact, in Chapter 8 will become a huge issue for us. And here's the type of issue that could come up. If it's the case that you're working with a set where the things in the set are actually equivalence classes for some equivalence relation, and folks, now anytime you're working with the rational numbers, that's exactly what you got going on. Think intuitively, whenever you're working with a set where the things in the set have different names to represent the same object, like the symbol 3/2 is meant to represent the same object as the symbol 6/4 in the rationals. Whenever you're in a situation like that, you are in danger of having trouble when you're trying to define functions from such a set to another set, maybe to the set itself. Okay. So what today's big punchline is anytime you're working in a set where the elements of the set could be represented by different symbols, like fractions, if you try to define a function from that set to some other set, you have to be careful that the function is what we usually refer to as well-defined. So on sets, for example, the rational numbers, and I'm going to start denoting the rational numbers by a capital Q with an extra line through it. Rational numbers, positive, negative, and 0. YQ, Q stands for quotients, it's quotients of integers, for which the elements are actually equivalence classes, are actually equivalence classes of an equivalence relation. Classes for an equivalence relation. There might be what we usually refer to as well-defined issues. Issues when trying to define functions from that set. From that set, which I could have phrased as when trying to define functions having that set as domain. You're scratching your head thinking, what the heck are you talking about? Here is an example. Example. I'm going to ask you to define a function. Define a function f from the rational numbers to the rational numbers. Here's the definition of the function. Hand me any rational number. Well, that's what a generic rational number looks like. And the rational number that I want you to spit out is take whatever's in the numerator, add 1, and divide by b. Okay? So nod your head saying that's no big deal. What goes in is a rational number. What comes out is certainly a rational number because this goes in, you're assuming a and b are both integers with b bigger than 0. What comes out is something in the numerator divided by something that's not 0, and the numerator's an integer, so you're thinking, well, it's no big deal. It is a big deal, and here's why. Note, f is not well-defined. Meaning, it's possible we can input the same rational number written in two different forms and the issue is different rational numbers may come out. Outputs may result. Here's the issue, folks. If you've presumably defined a function from the rational numbers to something else, here to the rational numbers, if you ask what comes out when you plug in 3 halves, all right. If you then ask what comes out when you plug in 6/4, better be the same output because 3 halves and 6/4 are the same rational number. But the issue here is, look, if I plug in 3 halves, what comes out? 4 halves. But if I plug in 6/4, what comes out? 7/4. So I've plugged in the same rational number, drawn or written or viewed from a different form or having assigned a different name to it. First the rational number 3 halves, then the identical rational number, although written differently, 6/4. And the issue is, for this particular description, what comes out is two different things. That's not allowed for a function because then you don't know what is it that actually comes out when you plug in the rational number. Well, what do you want to call it? 1.5 for a minute? I don't know the answer. Why is it not well defined? Since, well, this is another example of a situation where in order for a function to be well defined, it has to be the case that regardless of how you describe a specific input value, that the same output value always has to come out. If I can show you just one situation where that doesn't happen, then the function's not well defined. Since, for example, if I plug in f of 3/2, I get 3 plus 1 over 2, which is 4 over 2, which is 2. But plugging in the same rational number viewed from a different form, or the way we usually say it is with a different name attached to it. Here's another name for the same rational number, 6/4. We get 6 plus 1 over 4, which is 7/4, and the point is that these are not equal. So this function is not well defined. So now all of a sudden you're a little bit nervous. Like, wait a minute, you mean every time I define a function from something like the rational numbers, I have to somehow make sure that the function's well defined? Technically, yes, but this certainly hasn't come up as an issue before. I'm playing it up because it will come up as an issue when we're looking at a specific set later on, for those of you that have seen this before, when we're looking at the collection of cosets of a group by a normal subgroup, that collection we're going to want to define an operation on, and we're going to need to be careful that the operation that we define on it is actually well defined. So here's what we'll do at the beginning of next time, and that you'll start doing for homework next time. We'll give an example. We'll give an example of a function, let's call it g, from Q to Q that is well defined, and we'll show you how to prove it's actually well defined. Okay, and we'll give a proof. So that's the sort of thing that you'll start seeing on the homework that comes up tonight. Okay, so here is typically how I will assign homework. It'll be on Monday. It'll be due the following week from Wednesday. So here's the assignment that's due Wednesday the 29th. In section 2, and those of you that have taken a class from me before know what the notation means. For those of you that haven't, I'm going to list out a bunch of problems. The problems that I list out are doable, but I certainly don't want you to turn all those in. I want you to view these as maybe a good place to look for additional problems to practice before an exam, or if you're trying to nail down a concept, to do a few more of those. The only two problems that I want you to turn in from this section are the ones that I'll circle here. Just problems 7 and 9. And in section 4, problems 1 through 18, the ones I want you to turn in are 2, 4, and 18. And I'm going to give you a sheet with 2 extra problems on it. Extra problems, and I want you to turn those in as well. And I'll pass that sheet out now. Anything that I hand out in class, I will also, I can't guarantee it'll be done immediately, but I'll also at least post on the course website. So if you're watching the videotape of this class and you're not getting the assignment in person, you can just go on and grab that. Okay, what we'll do on Wednesday right at the beginning is vote as to whether or not you want to have a note-taking co-op in here. Let's see, did that sheet with emails, and I'll take that. Did everybody get a chance to sign the email roster? Take that, thank you. For those of you that might be off campus tonight and watching the video, if you could email me abrams@math.uccs.edu with your email contact information, that would be great, especially if you're going to perhaps not be in class quite often, then I need to be able to get in touch with you. And that's it for tonight, folks. If I don't see you before then, I'll see you on Wednesday. A snowstorm, or I have to cancel class one day or something like that. It should be on those dates. You'll know 2 weeks in advance when the exact date's happening. It's not any sort of mystery. But so I can't say on day 1 exactly when they'll be, but I'll give you plenty of advance notice so that you can prepare for those. Exam 3 will be essentially just another 75-minute exam. It'll cover the last third of the course, but it will be given during the final exam period in here, which happens to be Wednesday, December 12th. It's also the case that during the final exam period, Wednesday, December 12th, if you so choose, you can also take a second 75-minute exam during that 2.5-hour period. That second exam will cover the material that was covered on exams 1 and 2 together. And the way it works is, in the end, each exam is worth 30%. But I've talked about 4 exams, so that doesn't make any sense. You have to count exam 3, the one that you take during the final exam period. And then of the remaining 3 exams, you count your best 2. So if you do really well in exams 1 and 2, there's really no reason for you to take this sort of optional final during the final exam period. You just walk in, take exam 3, and leave. But if you don't do so well in either exam 1 or exam 2, you have sort of a chance to make it up at the end. I'll talk about this more in a little bit. That's, the nature of this course is sometimes it takes a little while for the sort of general idea to sink in, and some students stub their toes on exam 1 and then just start, the light sort of goes on in week 6 or week 10 or something like that, and so this sort of gives you a chance to maybe make that up at the end. Okay. Yeah, and let's see, it says here, I'll explain this in more detail as the final exam date draws nearer. Don't miss an exam. I mean, in effect, if you miss an exam, folks, then you're obligated to take this final exam. That's how you make up. So I'll just count it as a 0, but you get to replace that 0 by whatever happens. The files, we'll go over that in class, but there's a, I don't know what the official rules are called, but the rules are actually in place for a good reason, because it might be the case, folks, that your face may appear on some video somewhere. I mean, if you're sort of face in front, it's not likely that will happen, but you know, if you get up or you're walking late or something, you might appear on an archived video for this class, and this just says, if you're uncomfortable doing that, then, I don't know, wear a mask or something, or sit in the back, or sit behind the camera or something. I mean, we're trying to make it so that, especially in a class like this where I know some of you have full-time jobs, or maybe you're already teaching in schools or something like that, and you get off work and your car breaks down, or the traffic's too bad, or you just got something that, work takes you out of town, something of that nature. At least this way you have the chance of, heading onto the internet and watching me yammer around. Whoever is going to be recording this class, Nick, I know it's going to be you tonight, but student is going to have to be sort of like, because I do this a lot. Anyway, it'll be fun. Okay, let's officially start. My name's Gene Abrams. Feel free to address me any way you'd like, whatever you're most comfortable with, either Gene or Mr. Abrams or Dr. Abrams or Professor Abrams, or I don't really care, whatever whatever sort of is most comfortable for you. There is a website that'll support this course. At that website, I'll try to sort of rig it that will link you directly to these video things, but there'll also be a direct access to the video stuff as well that I'll talk about on Wednesday. I'm officially in my office before class for essentially a half an hour, and then it takes me about 10 minutes to wander over here, so if you're in my office, we'll sort of break at 4:20 to walk to class. I'm also in Tuesdays and Thursday afternoons for a couple of sessions. I actually teach a class in between those two sessions. That's why there's a chunk in there. And every day by appointment, so if you need to see me, please feel free to stop by. Or probably the best thing to do is send me an email and try to make an appointment, and then I can guarantee that I'll be in my office at a set time. Also, for what it's worth, and this seemed to be popular 2 years ago when I taught a class in here, I'd go right from here to the bus stop, because there's a city bus that I take home, leaves at 6:05, so there's like 20 minutes or so in between. So if you want to sit with me at the bus stop or something, just grab me after class for 10 minutes right outside here. I'm more than happy to answer any questions you might have or point you in the right direction on a problem you might be working on. So please feel free to take advantage of that. This supplemental instruction sessions with Jen Holmes, I'll talk about those more, especially in the context of homework and exams. So let's hold off on that momentarily. The text is, let's see, is this one? Yeah. Text by Fraley. It's a classic by now, actually. I think the first edition was 30 years ago or something, and he has updated it appropriately. He includes some stuff about cryptography and various interesting questions about algebra that have come up over the recent years, some of which have been solved. We'll talk about some of those over the course of the semester. There, I know, is like a international version or something like that, or something you get out of London that's a little bit cheaper. Someone showed me that actually last year when I taught this course, and it seemed to be identical, but there's no guarantees if you try to buy something that's a little bit non-standard. Plan on 3 exams in here, and here's how they will work. There'll be 2 standard 75-minute exams, exams 1 and 2. I list the approximate dates that those will be on. Approximate means, barring, if you know some friends in here, or probably most appropriately, if you go to some of these supplemental instruction sessions and you wind up working with someone in there, you might say, hey, let's do this assignment together. And if it's a mutually agreeable situation, then great, and if not to worry about it. If you decide to work together for one assignment and you turn that one in and you decide that just didn't work out very well, then fine. The next time you can just turn them in yourself. So there's no, you can sort of mix and match as you see fit over the course of the semester, whatever you'd like to do. The homework will be graded on a 10-point scale. That means that you're going to turn in a certain body of work, and there won't necessarily be 10 problems, but I will grade it out of 10 points, 10 being the maximum. When you do the homework, I'm going to pass around some information about what I expect to see when you turn in a homework assignment. What I'm looking for is complete answers. I'm looking for a strong indication that you really understood what the issue or the essence of the question was, what the tool or technique to get to the solution is, that you've written it up clearly, not clearly in the sense that, well, the instructor will understand what I'm talking about, so I'll just sort of scribble something down and let him figure it out. Clear in the sense that your homework solution should be written in such a way that if your solution was to be included in a student solution manual down the road, that it would fit that bill well. That some other student who presumably doesn't know what's going on would be able to read through your solution to a given problem and say, oh, now I understand what's going on. Okay? So I write up and give you lots of detail about how to turn it in, what it should look like, what sorts of things you should be wary of or sort of be on guard for. My philosophy on the homework is anything goes. I mean, almost literally anything goes. If you want to work together, it's final. Okay. The most important thing that you can do in here to prepare for the exams is to do the homework in such a way that you really understand the material. So here's how homework and a few short quizzes are going to work in here. The way homework, or the rhythm of homework will be this. I'll give you an assignment essentially every Monday. The assignment will include problems that I'll cover that Monday and probably the following Wednesday, so that week's worth. You should start on those right away. Admittedly, not all of them might be familiar because some of them cover. And then you, in effect, have a week to do the assignment. It'll be due the following Wednesday. Okay? So stuff that I assigned today will be due a week from Wednesday. Yeah. So I've tried this two different ways, and this is the first semester I'm going to try a little hybrid. So up until a couple years ago, it was always do the homework by yourself in the sense that I want you to actually write up your own homework assignment, turn it in. I always encourage you to work with other people, and I'm still going to encourage you to do that, and I'll talk more about those details in a minute. But if you'd like to work together in a group of either a group of 2 or a group of 3, and you'd like to, as a group, submit one assignment from your group in such a way that, when I grade it, everybody in your group will receive that same homework score, that's now going to be fine. And you can sort of mix and match groups. You just make sure that at the top of the paper you'd write down, this assignment is from this person and this person and this person, maximum of 3. So if you feel like you're better off understanding material by working together in a group, more power to you. That's good. If you feel like you're better off working alone, good for you too. So